Hi, future teacher. Need a math refresher lesson to get prepared for your teacher certification exam? If so, you found the right spot. By the end of this lesson, you will be totally ready to tackle the patterns and algebra questions that you will likely receive on test day. But don't stop here. Get full access to the study guides, video lessons, and practice tests that makes passing your teacher certification exam simple by visiting teacherpreps.com.
In this video, we're going to talk about the relationship between dependent and independent variables. A variable is a symbol or letter that represents a value that can change. It's like a placeholder inside an equation where we can plug in different values. There are two types of variables. Independent variable, that's known as the input. That is the quantity inside the equation that we change. The other variable is the dependent variable, also known as the output. That's the answer that we get. It's the quantity that changes because of the input that we put in. Think of it this way. The output depends on what we plug in for the input. Many times in math, we have data sets that contain two or more quantities written in an equation form. An example would be y equals 3x plus 4. The x is the input. We're going to plug numbers in for the x. And then our y is the output. That's our answer. If we plug a different number in for x, our output will change. Let's go through some examples together and figure out what our equation would be, what the independent variable is, and what the dependent variable is. This problem says you make $12 per hour. Our equation would be y equals 12 times x because it's $12 for every hour. Our independent variable is going to be x. That's the amount of hours we work. Our dependent variable is what's going to change based off the hours worked. That's the money made and the variable y. So your income, which is the output, depends on how many hours you work, or your input. Your income changes as you work different amounts of hours. For example, how much would you make if you worked 4 hours? If you worked 4 hours, we could put 4 as our input. Then 4 times 12 equals 48. 48 would be our output because that is how much money we made. This next example says that you can drive 60 miles per hour, which means you drive 60 miles every hour. You have already driven 200 miles. Let's write our equation. In this case, I'm going to use the variables m for miles and h for hours. So we have the amount of miles driven is going to be 60 miles for every hour, or 60h, but we've already gone 200, so we can add that 200 to our total. In this case, our independent variable is what's going to change. That's our h, or our hours driven. Our dependent variable is what's going to change based off of our input. The dependent variable is going to be the total miles, and the variable m. The amount of total miles driven changes based on how long you've been driving. For example, if we drive for 2 hours, how far have we gone? Well, if we drive for 2 hours, we can plug that in for h. That's our input. We would have 60 times 2, which is 120, plus the 200 miles we've already gone. When we add 120 and 200, we get 320 miles. That's our output. Go ahead and pause the video and try this last one on your own. When you're ready, hit play and we'll see how you did. This last one says that you can make 4 paintings every day, and you already have 3 paintings done. You can use whatever variables you want in this problem because it doesn't specify. I'm going to use a D for day and a P for paintings. So the amount of paintings we have is going to be 4 paintings for every day. And then we already have the 3 paintings done that we can add. The independent variable, or the input, is going to be days. And our dependent variable, or what's going to change based off the amount of days, is going to be the total paintings. What this is saying is that the amount of paintings you have changes based on how many days you make them. In this video, we're going to recognize and create equivalent algebraic expressions. First, let's go through some vocabulary. The first word is terms. Terms are part of an expression. 4x plus 2 is an expression. 4x is a term, and 2 is a term. Terms are separated by addition and subtraction signs. The next word is like terms. These are terms that have the same variable to the same power. 2x and 3x are like terms because they both have an x to the same power. 3m squared and m squared are also like terms because they both have an m to the second power. And finally, 2 and 7 are like terms. Neither one of them has a variable. Those are both constants. Constants are numbers without the variable. So 2 and 7 are constants. An expression is in its simplest form when there are no like terms or parentheses. The first step in creating equivalent expressions is to combine like terms. When we combine like terms, we want the sign in front of it to go with it. So for example, a minus 10 is really the same thing as a negative 10. The first thing I like to do is start with the variables and box the like terms. So we have a negative 3x and we have a positive 13x. Remember, include the sign that is in front of the number. So a negative 3 and a positive 13 makes a positive 10x. Next, let's look at the constants. We have a minus 10 and a plus 15. Minus 10 is the same thing as a negative 10. So negative 10 plus 15 is a positive 5. Now, since we're writing an expression, we have to have a sign in between our two terms. Since it was a positive 5, we're going to put a plus. Had it been a negative 5, we would put a minus sign in between them. So 10x plus 5 is the expression above in simplest form. Pause the video and try the next one on your own. Now let's see how you did. You should have gotten 7t squared plus 6t plus 18. We may also have to use the distributive property when we combine like terms. Recall that the distributive property is when you have a number multiplied by an addition or subtraction expression. In this case, we can distribute that 4 to each term. 4 times x is 4x. And then 4 times a positive 3 is a positive 12. Again, we're writing an expression, so you have to have a plus or a minus in between your terms. Pause the video and try the next one on your own. Now let's see how you did. You should have gotten negative 15x plus 40. Now let's put it all together to decide if we have equivalent expressions. We want to know, does the side on the left equal the side on the right? To determine this, we have to simplify each expression and see if they are the same. We have to first distribute this negative 4 through. So we have negative 4 times 2, which is negative 8x, and negative 4 times 8, which is negative 32. We also have this 3x to bring down. If you notice, we do have like terms. We have 3x and a negative 8x. 3 minus 8 is negative 5. So we have negative 5x minus 32, and the side on the left is in its simplest form. Now let's work on the side on the right. Negative 9x and positive 4x makes a negative 5x. Then we can combine our constants. Negative 24 and negative 8 makes a negative 32. You can see the side on the left equals the side on the right, so they are equivalent expressions. Pause the video and try the next one on your own. Now let's see how you did. When you have a negative in front of parentheses, you have to distribute that negative through. It's like multiplying by a negative 1. Negative 1 times x is negative x, and negative 1 times 12 is negative 12. We have the 4 to bring down and the minus 18x to bring down. Now we have a negative x that we can combine with a negative 18x. That gets us a negative 19x. And 4 minus 12 is negative 8. Now let's look at the side on the right. We have to distribute the negative 3 through. That gets us negative 3x, and negative 3 times 4 is negative 12. Now we have to add 16x. Negative 3 and positive 16 make a positive 13x. And then we have this minus 12 with nothing to combine with. Are our two sides equal? The answer is no, and we do not have equivalent expressions. In this video, we're going to find equivalent expressions for equalities and inequalities. Being able to find equivalent expressions is key when solving equations and inequalities. Equivalent expressions appear different, but are in fact equal. What this means is that if you solve the expression, or if you have a variable that you plug a number into, both answers will be the same. Here are a few examples. If you have -2 plus 4, we could rewrite this. Recall that a negative and a minus mean the same thing. So as long as the signs are the same on both expressions, then they are equal. So we could rewrite -2 plus 4 to equal 4 minus 2. We could solve these and see that they are in fact equal. -2 plus 4 is 2. And 4 minus 2 is also 2. If you notice, we have a -2 and a -2. And then the 4 is positive, and the 4 is positive. The two expressions are equal. Another example is 3/4 and 0.75. A fraction is the same as division. If you take 3 divided by 4, you would get 0.75. Also, think about this in terms of money. A quarter is worth 25 cents. You have 3 out of the 4 quarters, so you would have 75 cents. When thinking about equivalent expressions, we also have the distributive property. Here's an example. If you distribute, 3 times x is 3x, and 3 times 1 is positive 3. You can also tell if they are equivalent if you plug a number in. If I say that x was equal to 2, I could plug a 2 in for x. 2 plus 1 is 3, and 3 times 3 is 9. 3 times 2 is 6, and 6 plus 3 is 9. 9 equals 9. Pause the video and rewrite the following so that they appear different but are still equal. Now let's see how you did. On this first one, you could rewrite this by switching around the 3 and the -5. The 3 is positive, so we can write a positive 3, and a negative sign and a minus sign mean the same thing, so we can make this a -5. -5 plus 3 is the same as 3 minus 5. Both get us a -2 for an answer. On the middle one, we could take 1 divided by 5, or we can find an equivalent fraction to tenths. 5 times 2 get us 10, so 1 times 2 is 2. That's read as 2/10. You could also write 2/10 as a decimal. So these two are equivalent. And then finally, on this last one, you could use the distributive property to multiply 2 times x, which is 2x, and 2 times -5, which is -10. In this video, we're going to talk about the slope of a linear function. Slope is a measure of the steepness of a line. When you're finding the slope of a line, you can use a technique called rise over run. Or, mathematically, you can find the change in y divided by the change in x. Sometimes a slope is positive, that's when the line is increasing from left to right, and other times a slope is negative. That's when the line is decreasing from left to right. Let's go through a few examples. This says to find the slope of a line that passes through the points 1, 2, and 6, 6. There are two methods to find the slope. The first is to use rise over run. What that means is that find the lower point and go up until you reach the same line that upper point is on. Since we're going up, that's the rise. And we went up 1, 2, 3, 4 units. So our rise is 4. Then we're going to draw a line from where we just left off to the point that's on the line. We went right. 1, 2, 3, 4, 5 units. Since we went right or forward, that's going to be a positive 5. So our slope, using rise over run, is 4 over 5. We can also find slope mathematically. Remember I said we could find the change in y over the change in x. Change means to subtract. So we need to take our two y values and subtract each other, and then divide by the two x values subtracted from each other. So on this ordered pair, we could say the 1 is x1 and the 2 is y1. We could say the 6, 6 has the x2 and the y2. So taking the y2 that's 6, minus the y1, that's 2, we get 4. We can then divide by the x2, which is 6, minus the x1, which is 1. 6 minus 1 is 5. On both strategies, we get 4 over 5. Both strategies have its uses. If you're given the graph, just counting the rise over the run is really quick and simple. If you don't have a graph and you just have the points, using the equation can be the best option. Let's go through another one together. This says to find the slope of the line that passes through the points 1, 9 and 4, 0. Since we have a graph, it's a lot easier to just do rise over run. We're rising up 1, 2, 3, 4, 5, 6, 7, 8, 9 up. And it's positive since we went up. And then we're running 1, 2, 3. But it's going to be negative because we ran 3 backwards. So the slope is 9 over negative 3, but we can simplify out by dividing a 3 out of both. That gets us 3 over negative 1. Now we could leave it as a fraction because typically slope is written as a fraction, but we can also take 3 divided by negative 1 to get a negative 3. Either one of these will work for our slope. We could also use the equation and find the change in y over the change in x. Well, we could take our y2 minus our y1, that'd be 0 minus 9, and then our x2 minus our x1, which is 4 minus 1. 0 minus 9 is negative 9, and 4 minus 1 is 3. Dividing out that 3, we get negative 3 over 1, which is negative 3. And you can see that no matter which option we choose, our slope is negative 3. This next problem says to find the slope of a line that passes through 9, 5 and 4, 5. If you notice, we have a horizontal line. Let's talk about what happens when we have a horizontal line. How many are we rising? If you thought 0, you're correct. We didn't go up any. And how many are we running? If you said 5, you're also correct. 0 over 5 is equal to 0. So in this one, our slope is 0. Anytime you have a horizontal line, your slope is always going to be 0. This one says to find the slope of the line that passes through the points 3, 2 and 3, 8. Now on the last one, we had a horizontal line. This time we have a vertical line. Using rise over run, we can count how many we're going up. We went up a positive 6. But how many did we have to run? We ran 0. Having a 0 in the denominator is not allowed. So anytime you have a 0 in the denominator, your slope is undefined. So vertical lines get you an undefined slope, and horizontal lines get you a slope of 0. In this video, we're going to talk about functions. A function is an expression, law, or rule that defines a relationship between the input and the output. For it to be a function, each input is paired with exactly one output. Functions define the relationship between two variables. One is the independent variable. That's the input. It's the number plugged into the variable in the function. The other is the dependent variable. That's the output. It's going to be the answer produced when a number is plugged into the variable. Think about it this way. The output depends on what we plug in for the input. Functions are extremely useful in both math and in real life. What we have is an equation where we plug the input in and the output is produced. An example in real life would be your income. We could have an expression where we plug in the amount of hours you work and then we get the output, your income. In math, one way we use functions is when we make t-tables to graph equations on a coordinate plane. So we have an input that we're plugging into a function and getting an output. Functions are written just as the one below and is read, the function of x is 3x plus 4. Find f of 4. This is our output. It's going to be what is produced when we plug the input into the expression for x. Since it's f of x, where the x is a 4. That means that's what we're going to plug in for x. X is 4. So we're going to take our function and do 3 times 4, since that's what it means when we have 3x, plus 4. 3 times 4 is 12, and 12 plus 4 is 16. Our output is 16. Let's go through another one together. So this is read, the function of h equals h squared plus 10. Find f of 6. So 6 is our h. 6 gets plugged in for h and is our input. We have 6 squared plus 10. 6 squared is 36, and 36 plus 10 is 46. So our output, when our input is 6, is 46. Go ahead and pause the video and try this last one on your own. When you're ready, hit play and we'll see how you did. Now let's see how you did. Our input for m is 8. So we have 0.5 times 8, which is 4, and 4 minus 3 is 1. So when our input is 8, our output is 1. In this video, we're going to graph and interpret systems of equations. A system of equation is two or more equations that share variables. When we have systems of equations, we can graph them and see where do they intersect. That's the solution. A system of equation can have one solution, no solution, or infinite solutions. If it has one solution, it's going to be two lines that intersect. If it has no solution, the two lines will be parallel. And if it's infinite solution, the two lines will be the same line. On this first problem, it says that a taxi driver charges $2 per mile plus $2 regardless of how far he drives. Another taxi driver charges $3 per mile and does not have an additional fee. After how many miles will the two drivers make the same amount of money? We're looking to see where these two graphs will intersect. The first thing we need to do is write an equation for how much money each taxi driver will make. Let's call the first one taxi driver A. We can make the total amount of money made y. Taxi driver A will make $2 per hour. We can write that as 2x. And then an additional $2 regardless of how far he drives, so we can add 2. Now let's write the equation for taxi driver B. Just like with taxi driver A, we want to know how much money taxi driver B will make. So we want y equals. But taxi driver B is going to make $3 per mile instead of 2. And then taxi driver B will not have an additional fee. So we don't have a number to add. Now that we have our equations made, we can graph both of them and see where they intersect. The x-axis is going to stand for the miles driven, and the y-axis is going to stand for money earned. When we graph equations, we want them to be in slope-intercept format. That's y equals mx plus b, where b is the y-intercept and m is the slope. The y-intercept is where the graph is going to cross the y-axis. So in this case, driver A's is going to cross at point 2. M is the slope, which is rise over run. And we want that to be a fraction, so we need 2 to be written as 2 over 1. That means we're going to rise 2 and run 1. Rise 2 and run 1, rise 2 and run 1. Now we can connect our dots and we have our line for driver A. Let's do the same thing for driver B. Driver B does not have a y-intercept, so we're going to start at 0. We need to write the slope as a fraction, so that's 3 over 1. So driver B's line is going to go up 3 and over 1, up 3 and over 1, up 3 and over 1. We can connect the points, and now we have driver B's line. Where do they intersect? You can see they intersect at 2, 6. So the question asks, after how many miles will the two drivers make the same amount of money? The answer is after 2 miles. After 2 miles, driver B is going to start making more money than driver A. Now pause the video and try this one on your own. Now let's see how you did. This one says that Luke can decorate 1 cookie per minute and already has 2 cookies done. June can decorate 1.5 cookies per minute and has not decorated any yet. After how many minutes will the two have decorated the same amount? Let's start by writing an equation for Lou. We can make the total amount of cookies made y. Lou can make 1 cookie per minute and already has 2 made. Dune, on the other hand, can make 1.5 cookies per minute and has not decorated any at all. So now that we have our equations made, we can graph them on the coordinate plane. We can make the x-axis minutes, and we can make the y-axis cookies. Let's start by graphing Lou's line. Lou's y-intercept is 2, and Lou's slope is 1, which can be written as 1 over 1. So we can go up 1, over 1, up 1, over 1. Connect the points, and we have Lou's line. June does not have a y-intercept, so we can start at 0. June's slope is 1.5. We need to make that an improper fraction before we graph it. June's slope is 3 over 2. So we're going to go up 3 and over 2. Up 3 and over 2. We can connect the points, and now we have June's line. Where do the two lines intersect? They intersect at 4, 6. So the question asks, after how many minutes? The answer is after 4 minutes. In this video, we're going to graph linear equations. When we graph linear equations, it helps if our equation is in something called slope-intercept form. Slope-intercept form is y equals mx plus b. In the equation, the slope is the variable m. Remember, slope is the same as rise over run. It can also be thought of as the change in y over the change in x. Also in this equation, the b is the y-intercept. This is where the line intersects or crosses the y-axis. Having a linear equation in slope-intercept form allows us to quickly and easily graph the line on a coordinate plane. This first problem says to graph y equals 3x plus 1. The first thing I like to do is state the slope and the y-intercept. To help us, we need to make sure we're in slope-intercept form. That's y equals mx plus b, where m is your slope. Since we are in the right format, we know that y equals mx plus b. In front of the x is 3, so our slope is 3. We always want to write slope as a fraction when we're going to go to graph. So 3 is the same as 3 over 1. We could play around with negatives and say that it's also the same as negative 3 over negative 1. This is going to help us as we graph our line. Then our b, or where it crosses the y-axis, is a positive 1. So when you go to graph this, you always start with the y-intercept. Plot the y-intercept on the graph. The y-intercept is 1, so I put a dot at 1. Then we're going to look at our slope. Remember, slope is rise over run. So we're going to rise 3 and run 1. Now we have our point. Now if we go back to our y-intercept, now we can go ahead and use the other format of our slope, where we played around with the negatives. From there, our rise is actually going to be going down because it's a negative 3, and then backwards 1 because it's a negative 1. You could keep going if you wanted to and make as many points as you want to, or until you run out of room on your graph. The final step is to connect your dots and then draw an arrow at both ends showing that it goes on in both directions. Go ahead and pause the video and try this next one on your own. Now let's see how you did. Our slope is what's in front of the x, that's negative 2. We need to write that as a fraction, so we can write that as negative 2 over 1. Playing around with negatives, we could also have it as 2 over negative 1. Both of them are equivalent to negative 2. If you notice, we did not have a plus b. There's nothing there. So in that case, our y-intercept is 0. So our first step is to put the dot at our y-intercept, which is 0. From there, we're going to go down 2 and positive 1. Down 2 and positive 1. We could then go in the other direction by going back up to our y-intercept, and this time we're rising 2 and going backwards 1, rising 2 and going backwards 1. Connect your dots and draw arrows on both ends. We have one final problem. It says to graph y plus 3 equals negative 3 over 2x. What do you notice about this problem? If you thought it's not in y equals mx plus b format, you're correct. We have to move this plus 3 to the other side so that we have just y equals. To do this, we have to do the inverse operation of adding, which is subtracting. And what you do to one side, you must do to the other. So rewriting it, we have y equals negative 3 over 2x minus 3. Now we have our slope, which is negative 3 over 2, or 3 over negative 2. We also now have our b. Our b, or our y-intercept, is negative 3. We can then put our y-intercept on our line and follow the directions of our first slope. Our first slope says to go down 3 and positive 2. Since we can't go in that direction anymore, let's use our other slope. Going back to our y-intercept, we can go positive 3 and then backwards 2. Positive 3 and backwards 2. Connect the dots and draw your arrows, and you have your line. In this video, we're going to graph quadratic functions. The graphs of quadratic functions are called parabolas. Here are some key features that we will work through when graphing quadratic functions. The first is the vertex. The vertex is either the highest or lowest point of the parabola, and it's where the parabola switches from increasing to decreasing and vice versa. Next, we have the x-intercepts. The x-intercepts are where the parabola crosses the x-axis. This one has 2, but a parabola may have 1 or even no x-intercepts. Next, we have the y-intercept. The y-intercept is where the parabola crosses the y-axis. Every parabola always has 1. Finally, we have the line of symmetry. The line of symmetry is the blue line, and it cuts the parabola exactly in half. Knowing these key features helps us graph quadratic functions. We can graph the quadratic function either by factoring or by completing the square. We're going to do one of each. First, we're going to talk about graphing by factoring. When you graph by factoring, you want it to be in factored form. We learned this in a previous lesson. In factored form, x squared plus 2x minus 3 is the same as x minus 1 times x plus 3. The first step in graphing this quadratic function in factored form is to find the x-intercepts. To do that, we want to find the roots, or we want to set each of these to 0 and solve. Let's solve the one on the left first. We need to add 1 to both sides, and we find that x is equal to 1. On the one on the right, we need to subtract 3 from both sides, and we see that x equals negative 3. These two roots are our x-intercepts. We can go ahead and plot these on the graph. Next is to find the line of symmetry and the vertex. To find the line of symmetry, we want to take the average of the x-intercepts. So 1 plus negative 3 divided by 2. That's the same as negative 2 divided by 2, which is negative 1. So we know the line of symmetry is at negative 1, meaning that the x value of the vertex is also going to be negative 1. We need to find the y value of the vertex. We can come back up to our factors and plug in a negative 1 for x. Negative 1 minus 1 is negative 2, and negative 1 plus 3 is 2. Negative 2 times 2 is negative 4. So our vertex is negative 1, negative 4. You can plot that on your graph. Our final step is to find the y-intercept. Our x is 0 when we have a y-intercept. So what that means is that we can plug 0 in for x and solve. 0 times 0 is 0, so those cancel. 2 times 0 is 0, so those cancel, and we're left with negative 3. So our y-intercept is negative 3. Now we can connect our points, and we have our parabola. Now we can graph by completing the square. The first step is to move this plus 8 by subtracting 8 on both sides. We have x squared plus 6x, leave a space, and it's going to equal -8. Now we're going to take half of 6, which is 3. We're going to square it and add that to both sides. That's completing our square. Next, we're going to bring down this first variable, the first operation, this 3, and we're going to square it, and then we're going to solve the other side. 3 squared is 9, and 9 plus -8 is 1. Next, we need to get rid of the square by square rooting. What you do to one side, you have to do to the other. That leaves us with x plus 3 equals plus or minus 1. We now can set it up so that we have x plus 3 equals 1 and x plus 3 equals -1. When we solve these, this is going to get us the x-intercepts. So we can solve the one on the left by subtracting 3, getting us x equals -2. And we can solve the one on the right by subtracting 3, and we get x equals -4. These are our x-intercepts. So we can plot those on our graph. The next step is to find our vertex. I'm going to rewrite this to have what we had before we square rooted. Our vertex is going to be the opposite of this term, that's -3, and the opposite of this term, that's -1. So our vertex is -3, -1. We can connect our points and we have our parabola. The two equations that we solved together had two x-intercepts. You can have two x-intercepts, one x-intercept, or none. The discriminant can help us determine the amount of x-intercepts. This is the discriminant, b squared minus 4ac. If b squared minus 4ac is less than 0, meaning it's negative, then there are no real roots, and there's no x-intercept. If b squared minus 4ac equals 0, then you have one real root, meaning that parabola touches the x-axis. And then if b squared minus 4ac is greater than 0, there are two real roots. That's like the two examples we did together. In this video, we're going to interpret graphs of linear equations, quadratic equations, and inequalities. As you're interpreting these graphs, one thing you can look at is the steepness of the line. Does it have a large slope, or does it have a smaller slope? We can also look for changes and trends. Sometimes you have a line that increases at a certain rate, and then has a zero slope, and then starts increasing again. We can look and see where a line is increasing, that's when it has a positive slope, or decreasing. And then we can determine solutions by looking at the graph. Let's look at the following graph. If you notice, the y-axis measures distance in kilometers, and the x-axis measures time in hours. What we have here is two trains, train A and train B. One way that we can interpret what's going on with train A and train B is by looking at the slope of each of the trains. Remember that the slope is the steepness of the train, or the change in y over the change in x. Let's first look at the slope of train A. To find the slope, you need 2 points on the line. 0, 0 is 1 point on train A's line. Now 35, 1 is not exactly on the line, but it's close enough to interpret the slope. What that means is that at 1 hour, train A has gone 35 kilometers. Now let's look at train B. We can use 0, 0 for train B as well. Then if you look, in 2 hours, it's gone about 35 kilometers. So train B has gone about 35 kilometers in 2 hours. Now to compare these, it's going to make it a lot easier if we can get it in 1 hour just like train A. So we can divide both of these by 2. So train B is going about 17.5 kilometers per hour. By looking at the slopes, you can see that train A is moving faster than train B. Now, let's look at another type of graph. This is a graph of a parabola. Unlike the last graph, a parabola does not have a constant rate of change, meaning the slope or the steepness of the line changes throughout the graph. In this graph, the y-axis is measuring the height of an object in meters, and the x-axis measures the time in seconds. At first, the object is increasing in height as time passes, but after a certain point, it hits the highest point of the graph and the line starts decreasing. Most likely, an object is thrown into the air and gravity is going to make it eventually come back down to the ground. One thing that we can look at is at what time the object changes directions. Well, you can see that happens at about 5 seconds. We can also look and see at what height does it change directions. In this case, we can approximate and say about 118 meters. We can even look at the slope at different points in our graph. For example, what is the slope between 0 seconds and 1 second? Slope is the change in y over the change in x. So between 0 seconds and 1 second, our change in y is 40 meters, and our change in x is 1 second. So it changes at a rate of 40 meters per second at that point in the graph. What about the slope between 2 seconds and 3 seconds? When you look at the change in y, from 2 seconds to 3 seconds goes from about 75 to 100. The difference is about 25 meters. And the change in time between 2 seconds and 3 seconds is 1 second. So between 2 seconds and 3 seconds, our slope changes about 25 meters per second. Which one is changing at a faster rate? If you thought between 0 seconds and 1 second, you're right, because 40 meters per second is a bigger slope than 25 meters per second. Let's look at one more type of graph. This graph shows the solutions that solve the inequality y is less than or equal to 2x minus 3. Everything in the shaded region makes it true, so let's try one. 3, 0 is in the shaded region. If you plug those points into this inequality and solve, it should be true. The 3 is your x value and the 0 is your y value. So plug the numbers in and solve. 2 times 3 is 6, and then 6 minus 3 is 3. Is 0 less than or equal to 3? It is. So you can clearly see that that's a solution. Now we can try one that is not in the shaded region to prove that it's not a solution. Let's try 1, 1. The x value is 1 and the y value is 1. So again, plug the numbers in and solve. 2 times 1 is 2, and 2 minus 3 is negative 1. Is 1 less than or equal to negative 1? No, so it is not a solution. We could also look at the line of the graph. Notice that it is a solid line. This is because the inequality has that equal to sign in it. That means that everything on the line is also a solution. If it did not have the equal to sign, such as less than or greater than, then the line would be dashed, and anything that would be on the dashed line would not be a solution. In this video, we're going to determine if we have parallel or perpendicular lines based off of our equations. Perpendicular lines intersect at a 90-degree angle. Parallel lines are the opposite of perpendicular lines. They will never intersect and will always be the same distance apart. When we have two or more equations, we can determine if the lines are parallel or perpendicular by their slopes and their y-intercepts. This first question says to determine if the lines are parallel or perpendicular. Well, as I just said, you can determine if lines are parallel or perpendicular by looking at their slopes and their y-intercepts. Because we're comparing slopes and y-intercepts, it helps to get them in the same format, which is y equals mx plus b. That's slope-intercept format because we're given the slope and the y-intercept. This first equation is y equals 2/3 x plus 4. It's already in slope-intercept format. We can easily see that our slope is 2/3, and we can see that our b, or our y-intercept, is 4. Let's go ahead and graph that at the right. We can start with our y-intercept being 4. Our slope is up 2 and over 3. We could write this as -2 over -3 to help us graph in the other direction. Now we can connect our dots and we have our first line. This second one is not in y equals mx plus b format. We can get it easily in y equals mx plus b format by adding 1 to both sides. Now we have y equals 2/3 x plus 1. Our m is 2/3, and our b, or our y-intercept, is 1. Let's go ahead and graph this. Since our y-intercept is 1, that's our starting point on the y-axis. We're going to rise over run, meaning we're going up 2 and over 3. We could also do -2 over -3 and go in the other direction. As you can see, our two lines are parallel. So what do you notice about our two equations? If you noticed that our slopes are the same, but our y-intercepts are different, you're correct. If you have the same slope and different y-intercepts, the two lines are going to be parallel. Let's go through another example. This one says to determine if the lines are parallel or perpendicular as well. Again, let's put it in y equals mx plus b format if we can. This first one is, our m, or our slope, is 1/3, and our b, or our y-intercept, is 2. So if we graph this, our starting point is 2 on the y-axis, and we're going to go up 1 and over 3. We could go in the other direction by going down 1 and backwards 3. Connect your dots and you have your line. This second one is not in the right format, but we can quickly get it there by adding 4 to both sides. So we have y equals -3x plus 4. Our m, or our slope, is -3. Remember, we need to write that as a fraction, so we can put it over 1. And our y-intercept is 4. So starting at 4, we're going to go down 3 and positive 1. Down 3 and positive 1. What do you notice about our two lines? They're perpendicular. Now, what do you notice about our slopes? Our slopes are negative inverses of each other, meaning one is positive, one is negative, and they're the reciprocal of each other. When trying to determine if lines are parallel or perpendicular, you can always graph them. However, you can also look at their slopes and their y-intercepts. If the slopes are the same and the y-intercepts are different, then you know the lines are parallel. But if the slopes are negative inverses of each other, then the lines are perpendicular. Today, we're going to learn about representing patterns, relations, and functions through tables, graphs, verbal rules, and symbolic rules. Let's first recall what a function is. A function is a relationship between one variable called the domain, or input, and another variable called the range, or output, where each input is paired with exactly one output. An example of a function in real life is that each state has exactly one capital. You don't have a state that has two capitals. That would not be a function. In math, a function looks a little bit different, but the premise is the same. Again, the definition is that each input has exactly one output. So in our example of a function using symbols, each input has exactly one output. When we don't have a function, we have an input, but that input has multiple outputs. Let's look at what a table of a function versus a relation looks like. When we have a table, it helps to make something called a mapping diagram to determine if it's a function or not. In this, we have the values of x and the values of y. For the x, we have a 1, 2, and 3. And for the y's, we have 1, 2, 4, and 3. Then we can start pairing our inputs to their outputs. We have a 1 with a 1 and a 1 with a 2. We have 2 with 2 and 2 with 4, and then we have 3 paired with 3. This is not going to be a function. The reason being is that we have an input that's paired with more than one output. The input, 1, is paired with the output 1 and 2. It's the same with our input of a 2. It's paired with more than one output, 2 and 4. Let's look at this next example. Our inputs are 1, 2, 3, 4, and 5, and our outputs are 2, 4, 1, and 3. So now let's match them. We have 1 pairs with 2, 2 pairs with 4, 3 pairs with 2, 4 pairs with 1, and 5 pairs with 3. If you look at our inputs, each input is only paired with one output, meaning there's only one line coming out of each of our inputs. So this one is a function. The key to this is to look at the x values in the table. Notice that the first one has 2 1s and 2 2s in the inputs, where the second one does not have any repeat inputs. Now that we've talked about the tables of functions, let's look at the graphs of functions. When we look at the graphs of a function, we can conduct something called the vertical line test. When you do a vertical line test, you're going to move a vertical line across the graph from left to right. If it's a function, only one point will be on the vertical line at a time. If it's not a function, 2 or more points will be on the vertical line at the same time. Here are some examples of how you can use the vertical line test. On the left, we have the two tables that we had above, and on the right, we have the points plotted on a coordinate plane. We can use that vertical line to see if we have 2 points on the line at the same time. And you see right here we do. This was where we had the input of the 1 and the output of 1, and then the input of 1 and the output of 2. If you keep going, then you can see that we have another spot where the vertical line test fails. Because it failed that vertical line test, this one was not a function. If you recall, that second table was a function. If I move that vertical line from left to right, we can see that there is never a spot where we have more than 1 point on that line at the same time. So the second one is a function. Now let's put it all together. We learned that a function has one input for each output. On the left, we have a function, and on the right, we have a relation. We have the same information in a table, a mapping diagram, and a graph. Let's take a look. On the left, we have that function, and we see in the table that each input has one output. However, when we look at the table with the relation, we see we have one input that has 2 separate outputs, the -1, 2, and the -1, 1. When we look at the same information in a mapping diagram, we see that each input has one output. But when we look at the relations mapping diagram, we can see the -1 is paired with that 2 and that 1. Now we can look at the same information on a graph. Looking at the function graph, using the vertical line test, we can see that there's only 1 point on the vertical line at a time. But when you look at the relation graph, you can see that there are 2 points on the vertical line at the same time. That's that -1, 2 and the -1, 1. In this video, we're going to solve quadratic equations by completing the square. A quadratic equation is a polynomial of the second degree, and it looks like the following. ax squared plus bx plus c equals 0, where x is an unknown variable, and then a, b, and c are numerical coefficients. This is called standard form. For us to complete the square, we need it to be in standard form. It would look like the following. 3x squared plus 2x plus 5 equals 0. When you're solving quadratic equations, you're looking to see what the values of x have to be for you to get an answer of 0. One of the uses of this is to see where a parabola crosses the x-axis. Let's go through an example together. The first step in completing the square is to get rid of the plus 3 by subtracting 3 on both sides. This is going to leave us room to complete our square. The positive 3 and negative 3 cancel. Now we can rewrite x squared plus 4x, leave a blank, and it equals -3. Now we can complete our square. The first step is to take half of the middle number, 4 divided by 2. We're going to square that. 4 divided by 2 is 2, so we have 2 squared. And we're going to add that to both sides. We have to add it to both sides to keep the balance. On this next step, we're going to write our parentheses. In our parentheses, we're going to write this variable. We're going to write the next operation. we're going to write this number and then our square. And it's going to equal negative 3 plus 4. Negative 3 plus 4 is 1. Now we have to solve this equation. How do you get rid of a square? You square root. So we have to square root both sides, because what you do to one side, you have to do to the other. The square root and the square cancel, leaving us with just the x plus 2. And the square root of 1 is actually a plus or minus 1. It's plus or minus because a positive 1 times a positive 1 is 1, and a negative 1 times a negative 1 is 1. So we have two potential answers here. So now we have to set our equation up so that x plus 2 could equal 1, and x plus 2 could equal negative 1. To solve this, we subtract 2 from both sides on both equations. On the equation on the left, we have 1 minus 2, which is negative 1. And on the equation on the right, we have x equals negative 3. So our two solutions are x equals negative 1 and x equals negative 3. As I said before, that's where a parabola is going to cross the x-axis. So it crosses at negative 3 and negative 1. Let's go through another example together. The first step is to move this plus 7. You do that by subtracting 7 on both sides. Now we have x squared plus 8x, leave a space, and it's going to equal negative 7. Now we need to complete the square by taking this middle number and dividing it by 2, and then squaring it. 8 divided by 2 is 4, so we're going to add 4 squared. But what you do to one side, you must do to the other. So we're going to add 4 squared to the other side. Now we're going to write our parentheses. This variable comes down. We write the next operation. We write our 4, and we square it. Then we solve our right-hand side. 4 squared is 16. So we really have negative 7 plus 16, which is 9. The next step is to get rid of the square, and you get rid of it by square rooting. What you do to one side, you must do to the other. The square root and the square cancel, leaving the x plus 4. And the square root of 9 is plus or minus 3. The final step in finding your solutions is to take x plus 4 equals 3, and then x plus 4 equals negative 3. Now we can solve by subtracting 4 from both sides. That leaves us with x equals negative 1 and x equals negative 7. And we have our two solutions. Pause the video and try this next one on your own. When you're ready, hit play and we'll see how you did. The first step is to add 3 to both sides. That leaves us with n squared minus 2n, leave that space, and it equals 3. Now we're going to take half of this middle term, which is 2, divided by 2, and then we're going to square it. 2 divided by 2 is 1, so we're going to add 1 squared to both sides. Now we're going to write our parentheses. The n comes down, we write the next operation, and our 1 comes down, and we're going to square it. And then it equals 3 plus 1 squared. That's 3 plus 1, which is 4. Next, we get rid of the square by square rooting. And what you do to one side, you must do to the other. The square and the square root cancel, leaving us with n minus 1. And the square root of 4 is plus or minus 2. The last step is to take n minus 1 and set it equal to 2, and then n minus 1 and set it equal to negative 2, and then solve them. We can add 1 to both sides. That gets us n equals 3, and then add 1 to both sides, and that gets us n equals negative 1. So our two solutions are n equals 3 and n equals negative 1. In this video, we're going to solve quadratic equations by doing something called factoring. A quadratic equation is a polynomial equation of a second degree. It looks like the following: ax squared plus bx plus c. X is the unknown variable, and a, b, and c are numerical coefficients. So you might have something like this: 2x squared plus 4x minus 6. There are a lot of steps to solving quadratic equations by factoring. So let's go through a few of these together. Let's factor x squared minus 8x plus 12 equals 0. The first step is to take the first coefficient times the last term. There's no coefficient on the x squared, so we can put a 1. So we're taking 1 times a positive 12. We're going to write that off to the side. 1 times 12 is 12. The next step is to write all the factors, meaning what can you multiply to get to 12? The factors are 1 times 12, 2 times 6, 3 times 4, and then we also have the negative values, because a negative times a negative is positive. So negative 1 times negative 12, negative 2 times negative 6, and negative 3 times negative 4. After you find all the factors, then you're going to add them. 1 plus 12 is 13, 2 plus 6 is 8, 3 plus 4 is 7, negative 1 and negative 12 is negative 13, negative 2 and negative 6 is negative 8, and negative 3 and negative 4 is negative 7. Our goal is to split up this negative 8x. So we want two factors whose sum is negative 8. If you notice, our negative 2 and negative 6 sum was negative 8. So we're going to use these two factors. We're going to create two binomials. The first term drops and the last term drops. Then, like I said, we're going to split up this negative 8x. Negative 2x and negative 6x combine to make negative 8x. The next step is to factor each one of those binomials. What can you divide out of both terms? It can be a number or a variable. Since we have an x squared and a minus 2x, there's no number that we can factor out, but we can factor out an x. Taking out an x from x squared leaves us with 1x, and then taking the x away from negative 2x leaves us with negative 2. Now let's look at the second binomial. The first thing is that you never want a leading negative number, so we know we're going to divide out a negative. Now looking at the 6 and the 12, you can divide a 6 from both. So we're going to actually divide out a negative 6 from both terms. That leaves us with x, and then 12 divided by negative 6 is negative 2. What do you notice about what we just got? If you notice that what we have in parentheses matches, you're correct. If you get to this point and they don't match, you've done something wrong. Now that we have them factored, we're going to take the outside numbers and make them one set of parentheses, and then we're going to take what we had in the other parentheses and go ahead and write that down. We have this equal to 0. We're trying to find what values of x can we plug in to get 0. So we're going to take each one of these and set it equal to 0 and then solve. So we can add 6 to both sides. That leaves us with x equals 6. And then we can add 2 to both sides. That leaves us with x equals 2. So the two values that you can plug in for x to get a value of 0 is 6 and 2. And we have now factored this quadratic equation. Let's go through another one together. The first step is to take 3 times negative 2. That gets us negative 6. Now we're going to list the factors out that get us negative 6. The factors are 1 times negative 6, 2 times negative 3, negative 1 times 6, and negative 2 times 3. There aren't any other factors, so now we can find the sums. 1 plus negative 6 is negative 5, 2 plus negative 3 is negative 1, negative 1 plus 6 is 5, and negative 2 plus 3 is 1. Our goal is to get the middle coefficient, so we want the 1. Negative 2 and 3 get us that positive 1. Now we're going to create two binomials. The first term drops, and the last term drops. And we're going to split up this positive 1x by a minus 2x and a positive 3x. Now that we've created our binomials, we need to factor them. This first one does not have a number that comes out, but we can divide out an x. That leaves us with 3x minus 2. This second one does not have anything that we can factor out, but we have to factor out something. So we can factor out a 1. By dividing out a 1, we're left with a 3x minus 2. After factoring, these match, which is what we want. Now we can take the outside terms and put them together, and the matching binomial, and we have one final step, to set them equal to 0. To solve for x, we need to subtract 1 from both sides, leaving us with x equals -1. On this one, we have to add 2, leaving us with 3x equals 2, and then divide by 3. So x equals 2/3. So our two solutions are x equals -1 and x equals 2/3.